Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is video 43, lecture 20, part B. And we are discussing hypothesis tests for variances. Last time we looked at how to do a confidence interval for the variance and how to do a hypothesis test for one variance. In this video, we're going to talk about the comparison of two variances. Unlike the means, we do not subtract or add variances. To get our test statistic, we want to compare variances by division. So if we start off saying sigma 1 squared equals sigma 2 squared, then if we divide both sides by sigma 2 squared, then we get sigma 1 squared over sigma 2 squared is equal to 1. So if the variances are equal, then this ratio is equal to 1. This is a lot simpler than trying to add two chi-squared distributions, which gives us a more complicated gamma distribution. So by doing this, we get a F test. So let's look at that. We had this theorem that we talked about in section 5.2 in chapter 5 somewhere last semester. If U1 and U2 are independent chi-squared random variables with degrees of freedom R1 and R2 respectively, so R1 goes with U1 and R2 goes with U2, then the ratio, we take the first random variable, divide by its degrees of freedom, and then divide by the second random variable divided by its degrees of freedom. We can rewrite this by inverting and multiplying fractions. We get U1 R2 over U2 R1. Okay, so that's another way you can write this if you prefer. I like to see the derivation form of this random variable, but this is easier to calculate. So this is an F. This ratio, again, they're chi-squared distributions. They're independent of each other. Then you divide each by its degrees of freedom, and then divide that result by the one by the other. And that gives you an F distribution with R1 degrees of freedom in the numerator. See, in the numerator I have R1 here, and R2 in the denominator, which of course is not what I have here, so some people may be confused by that, but it's the degrees of freedom of U1 that goes first, and the degrees of freedom of U2 that goes second. All right? Now, so this is an F distribution, and R1 degrees of freedom in the numerator, R2 in the denominator. Now, we need to recall the reciprocal property of an F distribution. Our table doesn't give us everything we need for these tests. So if I have F of alpha, a 1 minus alpha, R1, R2, if that is in my table, but I need F of alpha, so 1 minus that, and I need R2, R1, so the degrees of freedom flip, then I take 1 divided by the F value I have. So whatever's here, I take 1 minus this. So 1 minus alpha, distribute your negative signs. You get 1 minus 1 plus alpha equals alpha. So I subtract this from 1, and then I flip these two, and that's the result I get by dividing by 1. So similarly, I like to do this other one just to give that to you so you don't have to think as hard, right? So if I have F alpha R2 R1, then I take 1 over that, and I get 1 minus this, so that's 1 minus alpha. And then I flip these two, or reverse these two, and so I get R1 R2. Okay, so again, this would be a value that you have in the table. This is a value that you don't have, that you want. And so that's how we use this reciprocal property. And we talked about this again back in chapter 5. So, confidence intervals for the ratio of two variables. So here's our data. We have two samples. They're size N1 and N2, and they're randomly selected independently. Okay, so the samples have to be independent. The easiest way for this to happen is if the two populations are independent, but that's not always the case. You can have dependent populations. Let's say you have family members within the two populations, so that they're related. So if you choose someone from one family in the first one, then you don't choose anyone from that same family in the second one. Okay, so that's one way to think about that. Family members are usually correlated, therefore therefore they are dependent and non-independent. Then, if you choose a family member in the first sample from the first population, then in the second population, don't include a member of that same family. Randomly select from the remainder. Okay. So that's one example of dependent populations and independent samples. Okay, so it depends on your situation. So we have population 1 and 2, and we have the population means, which are mu1, mu2. The population standard deviations are sigma I squared. The sample sizes, ni, or n1, n2, and the sample means, x bar sub I, and the sample variances, s sub I squared. Again, samples selected independently imply that S1 squared is independent of S2 squared, and it also implies that X bar 1 is independent of X bar 2. So remember that each of these is also a random variable. Okay? We call them, their distributions are called a sampling distribution of the variance or the sampling distribution of the mean for the X bars. And so let's talk about that. If both populations have normal distributions, again, this is required to use this. If you're testing about variances, the underlying populations have to be normal. Have to have a normal distribution. Otherwise, this method is no good. And it is very sensitive to deviations from normality. Okay? So, U1, let's say that's N1 minus 1, S1 squared over sigma squared. Last time we reminded you that this has a chi-squared distribution with N minus 1 degrees of freedom. And this will be, since S1 squared and S2 squared are independent, then these two quantities, these two ratios, will be independent. And so this same ratio, but for the second sample, we'll have a chi-squared with N2 minus 1. And by the theorem, then this ratio, U1 over its degrees of freedom, U2 over its degrees of freedom, and we substitute in for U1 and U2 here. And what we see is, so here is N1 minus 1, N1 minus 1. N2 minus 1, N2 minus 1. So those cancel out. Remember, this numerator can be written as N1 minus 1, S1 squared over sigma 1 squared, and then the denominator is written as, so this is N1 minus 1, which can be written as divided by 1. So this is going to be N1 minus 1, S1 squared over sigma 1 squared, 1 over N1 minus 1. So denominator, numerator cancels, gives us S1 squared over sigma 1 squared, which is exactly what we have here, and a similar result in the denominator. So, little basic algebra there. And so we can rewrite this as S1 squared over S2 squared times sigma 2 squared over sigma 1 squared, and this has an F distribution with N1 minus 1 and N2 minus 2 degrees of freedom. So again, these assumptions, these are requirements, is the other way to say this. When I first learned statistics, this wasn't, not when I first learned it, but when I refreshed my self on statistics after many years, this wasn't made very clear. It was made clear the first time around. It wasn't made clear the second time around. So I want to make it clear that this test only works if both of these assumptions are met. Otherwise, you need to use a different method, probably a non-parametric method. So the populations are independent, or the samples, I should say, samples are independent. Both samples, or, well, I can say populations there. Both populations are normally distributed. If the population is normally distributed, then the samples have to be normally distributed. Okay. Because we're not using means again, the central limit theorem does not apply. So it doesn't matter what sample size you have. The underlying data for a variance has to be normally distributed or approximately normally distributed, or else your results are not valid and you can't trust them. Okay. So let's derive the confidence interval. Since I did a non-symmetric confidence interval derivation last time, I won't go through this as in detail, or I won't write it out as we go. I've written it out for you so you can look at this, but let's walk through it. So we're talking about an F distribution. So this function is an F distribution. And for each combination of the degrees of freedom, we have a different distribution. So there's an infinite number of lines here for an infinite number of sample sizes. So we want to choose this point F1 and F2 so that in between them is 1 minus alpha degrees of freedom. And we want this to be as centered as possible. So since we want 1 minus alpha in the middle, and this only goes to 0 is the lowest value F can take. So that means that between this number, F1, and 0, there has to be alpha over 2 as a probability. And then for F2, we want alpha over 2 above it, and that leaves 1 minus alpha in the middle. Okay. Since it's a skewed distribution, we can't use the mean of the distribution anywhere in here, or the median. For a skewed distribution, the mean, median, and mode are all different values. For a symmetric distribution, they're all the same value. Okay. So we rewrite our test statistic, which was, what did we call it up here? Did we call it, we didn't call it anything. Did we call it anything? We didn't. Nope. So just our test statistic, U1 over R1, U2 over R2. We came up with this formula here, and F1 and F2. Now, F1, I'm going to write it as a critical value. Then I need to know how much is above it. So that's going to be 1 minus alpha over 2. So this is going to be an F subscript 1 minus alpha over 2 with N1 minus 1, N2 minus 1 degrees of freedom. Likewise, F sub 2 has alpha over 2 above it. So it's going to be F sub alpha over 2, N1 minus 1, N2 minus 1. So I'm going to substitute that in for F1 and F2 into my equation. It makes it a lot messier looking. You could leave F1 and F2 in here until you got done and then substitute in if you'd like. That's fine too. And what I want to do is I want to isolate. I want sigma 1 squared over sigma 2 squared. In order to get this, I have to invert. I have to put everything under 1 or flip a fraction. And so that's what I've done next. So I've used the reciprocal of all three sides. So notice that this is flipped, so it's S2 over S1. And this is flipped, and it's sigma 1 squared over sigma 2 squared, which is what I want. Now I can just divide by this quantity, all three sides. Dividing by that is the same as inverting and multiplying. So I end up with S1 squared over S2 squared, right? If I multiply by S1 squared for S2 squared, this and this cancel out. So this is going to be S1 squared over S2 squared. S1 squared over S2 squared. And that's what I have here. And so I can rearrange this however I'd like. So when I flipped it, remember I had reversed the signs. I had to reverse the signs when I inverted here. And so what I do now is I just flip the inequality. And so I have the small number over here, then the quantity I'm looking for, and then the larger number over here. This is the 100 times 1 minus alpha percent confidence interval for the ratio sigma 1 squared to sigma 2 squared. Now, if sigma 1 squared is equal to sigma 2 squared, then I divide both sides by sigma 2 squared. Sigma 1 squared divided by sigma 2 squared is equal to 1. So that is what I'm testing, that f, or that this quantity is equal to 1. And if I want sigma 1, the standard ratio of the standard deviations, take the square root. And you'll notice what I've done here is I've taken S2 squared. You could leave it in the numerator, but how we normally do it is, in the calculator, we probably do it more this way. It's less parentheses. So I put S2 squared in the denominator and did the same thing here. So we have some cases here. If sigma 1 squared is equal to sigma 2 squared, as I've mentioned, the ratio is equal to 1. But what if we don't want that ratio? What if we want not just 1? We want the ratio, but we want the ratio to be equal to some constant. I call it C0 just instead of having confusing, notation. So some constant, C0. Then this ratio equal to that value means that it's the same thing that sigma 1 squared is C naught times sigma 2 squared. Okay? So our test statistic is going to be the sigma 1 squared over sigma 2 squared times, S1 squared over S2 squared times sigma 2 squared over sigma 1 squared, the inverse. So kind of different, and we've shown that that's an F distribution. So we have this example where we wanted to show, originally we went over this before, where there's two adhesives and we have the information, and they wanted to show that the first adhesive was superior to the second. But now what we want to do is we want to first test for the quality of variances between the two adhesives at alpha equals 0.05. And then based on part A, which test should we use for testing mu1 equals mu2? This is how we actually do it. We do the test here first, then we would determine which test to use. So we're not just blindly doing what we were showing in section 8.2. We have a method. So we want to calculate a confidence interval for the ratio of variances, and then we want to do it for the standard deviations. So let's get started with that. I have sigma 1 squared equals sigma 2 squared. That's that they are equal, right? And so, because equal, ratio is equal to 1. And then this would say sigma 1 squared over sigma 2 squared is not equal to 1. So this means that sigma 1 squared over sigma 2 squared is equal to 1, and sigma 2 squared over sigma 1 squared is equal to 1, right? So whether you flip 1 and it's still 1. All right. So our test statistic is going to be S1 squared over S2 squared, sigma 2 squared over sigma 1 squared. Now, we just said that this ratio is 1. That's why most texts, they're only looking at the equality of variances. So they say this is 1. When it's equal, that's true. And then this cancels out. This goes to 1 and just leaves me S1 squared over S2 squared. I'm given the squares here. See, I'm given the squares, so I don't need to square anything. 24, 633 over 35, 475 equals 24, 633 divided by 35,475 gives me 0.6943 . I'm going to do this to 3 decimal places. 0.694 is going to be my test statistic value. My rejection criteria, because I have a not equal to, I have to do F observed less than F 1 minus alpha over 2, N1 minus 1, N2 minus 1 degrees of freedom, or F observed is greater than F sub alpha over 2, N1 minus 1, N2 minus 1 degrees of freedom. Okay. So this F is 1 minus, we're doing 0.05, so that's alpha over 2 is 0.025, and 1 minus alpha over 2 equals 0.975. So this is F of 0.975. N1 is 22, N2 is 24, so this is 23 and 23 degrees of freedom. And this is going to be F of 0.025, 23 and 23. Let's look at our table. Oops, that's not where I wanted. Let's go back to our tables, look at the F distribution, F table. Now, so they have nice pictures here showing what's what, and this is the numerator degrees of freedom. It only goes up to 10 on the first one, so I need to keep going. Still 10 now. Okay. I only have 24 or 20. Okay. So at the same degrees of freedom, let's see, this one is bigger. What I want to do is I want to go to 20. I always round down the degrees of freedom. So the degrees of freedom that's closest to this but lower than what I have. So instead of going to 24, I'm going to go to 20. And I need 20 in the denominator as well. Well, in this first table, it only goes to 9. In the second table, we have it. So we'll have 20 and 20. And we want the alpha is 0.025. So this is the value we're going to use. This is going to be F of 0.025, 23, 23. That's what we're going to substitute for it. So 0.025, so we have this value, and what was it? I've forgotten now. 2.46. So this is 2.46. So F observed, which is 0.694, greater than that, that's not true. Now, in order to get this, I don't have this in the table. If you look at the table, it has alphas of 0.05, 0.025, and 0.01. Nothing else. So that means that F of 0.975, 23, 23 will equal 1 over F of 0.025, 23, 23. Since they're the same degrees of freedom, numerator, denominator, I switch them, I get the same. So this value, so I use 20, so I'll use 20 here again. So that is going to be 2.46. So 1 over 2.46. And that gives me a 0.4065. So 0.407, and I have 0.694 less than 0.407. Neither one of these is true. So I do not, or I fail to reject H naught. Now, let me explain that most of the time we want the variances to be equal. In this case, it makes the test much easier. We don't have to use Welch's t-test. We can use the other test where we use the pooled sample variance. for the means, for testing the means. So we fail to reject the H naught. That means do not reject H naught. Same thing, right? We've got a naught here. We need a naught here. Does not exist sufficient evidence to support the claim that the variances for the force required to separate adhered pieces or glued pieces is different for the two adhesives at a 98% confidence level. Did I use 98? This was 95. I'm sorry. Where is it? Here we go. At a 95% confidence level using N1 equals N2 equals 24 glued pieces or adhered pieces. So N1 plus N2 equals 48. Just remember that. Both of these are equal to N1 is 24 and N2 is 24, and they're different. Okay. So based on the result in Part A, we can assume equal or common variances, so we can use the test statistic T observed as this with the pooled variance. Okay. So to do that, so this is all that was asked. Right? I didn't ask you to do it. I said, based on this, which test should we use? So we can use this test statistic with this degrees of freedom. You need to tell me both. Test statistic and degrees of freedom. You need both of those to tell me which test it is. And I've done that by saying that this has a t distribution with N1 plus N2 minus 2 degrees of freedom. This has to be true because the data has to be normally distributed since N1 and N2 are less than 30. Okay, so it's not approximately. If N1 and N2 less than 30, then it's approximately by the CLT. Now Part C says calculate a 95% confidence interval for sigma 1 over sigma 1 squared over sigma 2 squared. So let's walk through this. We write down the formula for the confidence interval. This is a little lighter than I thought it would be. Okay, so we have that. Alpha is 1 minus C. C is here. This is C. So this is 0.05. I need alpha over 2. That's 0.025. And 1 minus alpha over 2 equals 0.975. So I have 0.025, 23, 23. Again, I'm going to use 20 and 20. I always round down because I didn't have, and we looked that up last time and it was 2.46. And so it says the larger F, larger CI when it's on the bottom for lower confidence limit. Okay. And then for this one where we have 0.975, for the upper confidence limit, we want to, if we have so we need 1 over what we had here, and because they're the same, the denominator degrees of the degrees of freedom are the same, and it says a larger F here is a smaller 1 minus F, which is a larger CI. So again, we use the 20/20. We use the same degrees of freedom. So when you round down the degrees of freedom for one, you're going to do the same thing for the other one. That keeps it from being confusing. We took 1 over that. We got 0.4065. Okay? All right. Now, we need to calculate the confidence interval. So I used 2.46 here and 0.4065 here. I plugged in the other numbers, and I came up with these numbers, and we round that to 0.282 and 1.708, so 3 decimal places. And if we use 24 and 24, look what happens. We get a smaller confidence interval, which we would like, but we can't trust it. We are not 95% confident that this one, we're less than 95. This would be less than 95% confidence. Less than. That's not good. We don't want to be less than. Okay? So we are 95% confident that the interval contains the ratio of variances of adhesive force of adhesive 1 to adhesive 2. That's important to say that it's 1 divided by 2. N1 equals N2 equals 24 adhered pieces. Since 1 is inside the confidence interval, we would conclude that there is no difference in the variances of adhesive 1 and adhesive 2. So when we're looking at these ratio, this number, this goes from less than 1 to greater than 1. When 1 is in these confidence intervals for the ratio, we can't say that there's any difference in them. And we had concluded that with the test before. And so for sigma 1 over sigma 2, here is the confidence interval. We'd simply take the square roots. And that is it for this video. So I hope this has been helpful. If you have questions, come to virtual office hours. If you need help before then, email me, but send me a picture of the problem so I know what you're working on, and a picture of your work so far, and that way I can help you efficiently. Please take care of yourself, because we hope to see you next time.